Hi, I'm Ben-Yaakov. This presentation is entitled Synchronous Sampling and Anti-Aliasing Filter, a demonstration by LTspice simulation. Now, this is not a mathematical derivation or explanation of the whole issue of aliasing and folding and synchronous sampling. It is an intuitive explanation using simulation just to get hold of what is really going on with the sampling and the folding and the aliasing, as well as the advantage of synchronous sampling. So I hope this will be helpful to some who are a little bit baffled by the whole issue, and this will give a better intuitive understanding of the whole issue. So here is a typical problem we are facing many times. Here is the system. In this case, it's a switch mode power converter. It has a switcher. It's a high power, high voltage, high current sometimes. And then we have, of course, an MCU, a microcontroller, that will control this whole thing. And it has an A to D for sensing and getting information from the system. And among them are sensors like temperature or current or many other sensors. And the problem that we have is noise injected into this line of the A to D, and therefore it's corrupting the data, and then the control could be affected by this. So this is the issue actually that is related to the question of aliasing and synchronous sampling. So here I've set up a LTspice simulation schematics to just demonstrate this whole subject. And what I have here is, first of all, a source of 10 Hertz. This should be like a sensor or some other source. And then I have added to it noise. It could be a square wave. In this case, it's a square wave. It could be sinusoidal. So we have a sum of these two. So it's some signal plus noise. Then I have a filter that I'm going to talk about. And then we have here a sampler, okay? And this is the driver of the sampler. And I am discussing a case of 1 kilohertz sampling rate and 10 microsecond width. This doesn't really matter. We have here a capacitor, which is like a sample and hold, so that when the sampling is on, then you get the voltage from this 1 microfarad capacitor to this capacitor. The voltage is captured here. Now, this is really related only to the schematics. In the microcontroller, this is not happening. I mean, there is a capacitor for sample and hold, but after that we have numbers, okay? Because then there is an A to D, and then we are dealing with numbers. So we are not interested, in the case of the microcontroller, in the waveform here. But I'm going to look at this waveform just for the sake of understanding what is the signals here, what is the spectrum. But again, I'm going to emphasize it later on. This is the spectrum of this point has to be looked at carefully, because in the microprocessor we are not interested in the waveform but in the numbers that we are getting after the A to D. So then I've also put here 1 microfarad capacitor, so it'll be a larger capacitor than this one, and this resistor is adjusted according to the breakpoint of the filter that I'm interested in. And for example, this the low pass filter here is 100K, so in this case it's quite a wide bandwidth, so actually it's not doing anything in this particular case, but I can change it, of course, to any frequency I wish with this param. And this is just for the model of the switch. So we are starting with an example of 10 Hertz signal, 20 kilohertz noise, and then 1 kilohertz sampling rate. So this is just as an example for the explanation. And here I'm showing the case of a synchronous sampling. I have here a signal which is corrupted because you can see here the noise riding on it. This is already the voltage on the sample and hold capacitor. This is the sampled signal. Again, we are not usually interested in this signal, but rather in the numbers that we are getting as we sample this waveform. But again, just for the sake of explanation, I'm showing it. And here is an expanded scale. What we see here is part of this signal here Here is the noise that I have injected, and you see that I'm sampling it right here, smack at this point. Now I'm sampling it at 1 kilohertz, but the noise itself is 20 kilohertz. Here it is. The period is 50 microseconds, so the noise is at a frequency of 20 kilohertz. So there is a synchronization between the sampling and the noise. This will be very typical of an inverter, for example, that is running, say, 20 kilohertz, and then you are sampling it. Synchronous with this doesn't have to be at 20 kilohertz, could be some number below that, but it should be a whole number, okay? So in this case, we are sampling it here. Now we are sampling at the same point. It's a quiet point. Transitions are here, like in an inverter, you have high transition here, high noise. We are sampling it at this point, so it's quiet. And in fact, in this portion here, let's say it's here somewhere, it's like constant. I don't see any noise because I'm sampling here at the same point. It is adding, by the way, some DC, but usually this is a small value, so we don't bother about it. So this will be a synchronous sampling. Now, if the sampling is not synchronous, and I've done this by changing the noise frequency to a bit lower frequency, it's 17 kilohertz as a matter of fact, and you see that the period now is 57 microseconds, and lo and behold, this is again the signal, the original signal, the noise riding on it, and here I'm sampling it, and you see there is quite a bit of noise, and the reason is that I'm sampling it at different points, not the same point all the time, okay? So here is an expanded scale. What we see here is the synchronous case, and this is the asynchronous case, or non-synchronous, and you see that since I'm sampling it at different times of the noise, I am generating a noise which is quite a bit, which is really very harmful, and therefore there is no question about this, that sampling synchronously with the noise, if you can do that, is very, very beneficial. So let me now move to the question of aliasing or folding, and which has to do with the Nyquist sampling criterion. Now, the Nyquist criterion says the following. In order to sample a signal and to be able to reconstruct it, or I'd even add to be able to work on it or filter it, or in general to handle it, you have to have the sampling high enough as compared to the frequency of the signal. Now, the criterion says that the signal should be at a frequency which is below half the sampling frequency. So this is the sampling frequency. In our case, it's 1 kilohertz. And here is 500 hertz is half of it. So Nyquist says that you can operate safely in this region up to half the switching frequency. Now, usually you don't want to get too close to it because it means that you have very few samples per cycles. So practically you go somewhere below that, but it's very important to be obviously below half the sampling frequency. Now the question is, of course, what happens if you have noise above this Nyquist frequency, okay, above this 1 kilohertz, or between the 1 kilohertz and 0.5 kilohertz, okay? And this is also a forbidden zone, I'd say, in terms of the Nyquist criteria. It should be always here. And this is what I'm going to demonstrate to see what is really happening. To understand what is the problem, I've sort of scribbled down here a signal with some noise to it. And the noise is close to the sampling frequency. This is supposed to show the sampling instances, okay? So as I sample it, you see that, so without the noise, I'm reconstructing this staircase type of a waveform. This will be on the sample and hold capacitor. But with the sampling, I'm starting to sample the noise at different points, which actually gives rise to a frequency which is lower than the noise frequency. And this is what we call the folding. So what really happens is if you have frequencies, say between 0.5 to the Nyquist frequency, let's say 700 hertz in our case, there'll be folding and you'll get a signal here in this region. So it's going back into your area, which is very bad because you cannot get rid of it by digital filtering anymore. Because once it is here, then it's part of this frequency range, and you cannot filter it out because this is the area you're working at. Okay, so this is very bad. Now, same thing happens when the frequency is above the Nyquist frequency, say in our case 1700 hertz. Then again you have this folding effect, and this now annoying signal is really very harmful, and you cannot get rid of it. So this is a real problem. So let's have a look at this by simulation. So I'm showing here the signal. This is 10 hertz, this is the spectrum, and here is the disturbance, this is the noise, 700 hertz. The sampling is at 1 kilohertz, and this is the signal before the sampling, okay? And this is the signal after the sampling on the sample and hold capacitor. Again, this is just for demonstration. And what we see here now, that we get a 300 hertz signal, quite high, below the 500 due to this folding. Because we have a difference of between 700 and 0.5 kilohertz. This is half the sampling frequency, which is 200 hertz. So 500 minus 200, this is to the other side, is 300. And this is where we are getting this signal. So this is really showing this phenomena of folding due to, in fact, undersampling of the noise. If the noise is higher than the Nyquist frequency, 1700, we are sampling at 1 kilohertz. Again, what you see this spurious aliasing signal, this folding effect, in which you have now two signals, one 700 and one 300, within the range of your interest, and there's again nothing you can do about it. It's corrupting your signal, and this is something very, very bad in a control system. Let me just go back for a second to the issue of the voltage across the sample and hold capacitor, which I've emphasized earlier, just to re-emphasize it, the following. Without noise, just sampling, we see in the spectrum, looking at the sample and hold capacitor, this spectrum, obviously we see the 1 kilohertz because of the sampling, the stir case, and then the harmonics of it. This is really not relevant to the whole issue of the digital control, because in the digital control we are not worried, or we're not concerned, or we're not handling this waveform, but just the numbers at the sampling. So disregard this part. It has nothing to do with the actual operation of the digital control. But just for the sake of explanation, I'm showing this spectrum, okay? This is the best I can think of. And so in this case, when we have noise, obviously this is this spurious noise, this is the folding effect, this is the 1 kilohertz, and here part of this has to do with this 1 kilohertz sampling, which is really not relevant to the whole issue. So just forget about this part and let's concentrate on this region, which is of interest, of course, and this is the region where our signal is in. So what is the remedy for that? Well, the solution is to put a filter, an analog filter, before the sampling. So you see that analog is still alive, okay? So here is the filter. It is put before the sampling. The idea is to get rid of the signal above the Nyquist frequency, so there will be no folding into the range that we are working in. Now, the lower the frequency of this filter, the better. Obviously, you're restricted with the signal that you have. So if I have a signal of, say, 10 hertz, I'd say a filter of 100 hertz would be okay. And here you see I've put here a breakpoint of 100 hertz. And this is to attenuate the 20 kilohertz that I have here. Well, it's not 20 kilohertz. This is just to introduce this non-synchronous case. This is actually 17.5 kilohertz, okay? So we are not sampling in a synchronous way. If you sample in a synchronous way, even in this case, you'll get rid of most of the noise, of course. So I'm demonstrating it sort of in the worst case. So here it is. I have here three cases. The first one is just the signal, no noise. What I see here is this 1 kilohertz switching and its harmonics. Again, this is the voltage across the sample and hold capacitor. It's really non-relevant to what we are talking about. So again, let's forget about it. So all what we see here is the sampling of the 10 hertz. Now I'm introducing this 17.5 kilohertz noise square wave. And the sampling is 1 kilohertz and there is no filter. This is the previous case that I've shown. Here is the signal, the spurious, the aliasing, and this is the folded frequencies. Very bad, corrupting this part here. And by the way, if the noise would have been a higher frequency, it would have penetrated even deeper. So this is very bad. Now I've put a filter in. It's a 100 hertz filter. It's first order, nothing fancy, and lo and behold, you see that it cleaned it up very, very nicely. Okay, so now we have the signal itself. Well, there's some spurious signal here. I don't know if it's a simulation or maybe it's a real signal. Anyhow, it's very, very low. It's something like minus 70 dB, which is very small and low power. So this shows the power of this analog anti-aliasing filter. So what are the conclusions here? To combat sampling noise, we first of all would like to sample synchronously with the noise if possible, and many times it is possible, like if it is a switch mode system. We are controlling the switching frequency, the sampling frequency with the microcontroller, and this is really possible. And another very important part is to put a low-pass anti-aliasing filter, and the filter should have a as low frequency as possible rejection so that you'll get rid of the high frequencies which are causing the folding. So this brings me to the end of this presentation. I hope you found it of interest, and I thank you very much for your attention.